We've seen titrations before. They use burettes. We use burettes to perform titrations that are useful for solving the concentrations of unknown acids or bases. Today, we're going to do something a little different. We're not just measuring concentrations, we're seeing how pH of an acid responds as we add a base, or how the pH of a base responds as we add an acid. We're going to create what's called a titration curve, and that's real chem. This is a pH probe. It's actually a tiny electrochemical cell that's got a pH-sensitive voltage. And right now, it's ready to measure the voltages of some strong acids and bases. I'll add this sodium hydroxide, a strong base, to this hydrochloric acid, a strong acid, a little bit at a time, and record the pH after each addition. This might take a little while. Notice how we start at low pH because we're measuring a strong acid, which ionizes completely. As we add the strong base, it reacts completely, neutralizing some of the acid. The pH depends directly on the concentration of the unreacted acid. The pH rises slowly at first, then shoots up as it nears the equivalence point. Why? That's when all the acid is neutralized, forming water and a neutral salt, and the solution rapidly transitions from being acidic to basic. And after that, the pH climbs gradually and levels off as we dilute the strong base. Now, let's flip the script. What happens when we titrate a strong base with a strong acid? Same process, different order. Here's our new curve. It's the mirror image of the first one. This time, we start at high pH due to our strong base. The pH gradually decreases due to the added acid, and it plunges near the equivalence point at pH 7 and leveled off at a low pH due to the excess acid. Chemistry loves symmetry. Let's reset and do another. This time, I'm going to titrate a weak acid with a strong base. But I'm tired of these manual burette operations that are super painstaking. I'm leveling up. Meet the drop counter, a robot that's here to save my wrist and my eyeballs, titrating with precision and speed. This is the Terminator of titrations. Whoa, don't point that thing here, little buddy. Here, we have a beaker filled with acetic acid, a weak acid, and a burette filled with sodium hydroxide, a strong base. My drop counter is going to record the volume and the pH at the same time. Let's get titrated. Notice how this curve has a higher initial pH than the strong acid. The weak acid only partially ionizes, so its hydronium ion concentration is lower, and pH is higher than the same concentration of strong acid. When we add the strong base, the reaction goes to completion, turning weak acid into its conjugate base. In the middle, there's a relatively flat area. That's the buffer region, where we've created a similar concentration of acetic acid and acetate. Here's the really cool part. Halfway to the equivalence point, the pH equals the pKa of acetic acid because we have equal concentrations of weak acid and its conjugate base. This lets us identify the acid if we know the pKa. At the equivalence point, the pH is above 7 because the reaction has converted all the acetic acid into acetate, which is a weak base. Let's try a new experiment. This is the final round. A strong acid, HCl, titrating a weak base, ammonia. Here, we start at a high pH thanks to our weak base, ammonia, and its hydrolysis. The flat region, that's the buffer zone, where the reaction forms ammonium. At the equivalence point, the reaction has converted all of our weak base into its conjugate acid. Because ammonium is a weak acid, and the pH here is below 7. After that, it's all just the dilution of our strong acid being added. When we look at all 4 titration curves, we see some fascinating patterns. Strong acid and strong base titrations are mirror images, with the equivalence point at pH 7. Weak acids and bases create buffer regions, and their equivalence points shift depending on the strength of the acid or the base. And the best part? Titration curves don't just look cool, they help us identify unknown acids and bases, predict buffering capacity, and understand chemical behavior in real time. Now that's real chem.